no nervousness, okay?
It's okay. Hello everyone, I'm Bhavna, and today I'll be presenting our work Cocoon, on-body microphone collaboration for spatial awareness. This is my internship work done with my co-authors at Nokia Bell Labs. There has been a significant rise in the number of wearable devices in the past years. We are all surrounded by wearable devices. All of us have smartwatches, earables, and maybe smart glass or rings. And the number of devices per person has also increased in the last decade, which means we have a number of wearable devices on our body. And with wearable devices comes a lot of sensors. And microphone is the most common sensor that can be found on almost all the wearable devices. And we already have a number of microphones on our body. There's a microphone on our earable, there's a microphone on our smartwatch. But their use has been, they are mostly used independently, and their collaboration has been very limited. But if we can somehow collaborate the audio streams from all these microphones that are present on our body, it can lead to a lot of exciting application. Because microphone collaboration offers this unique opportunity because all these microphones are on our body and sensing the same phenomena from multiple vantage points. So this can lead to a variety of applications like reliable sensing, sensor selection, signal enhancement, and a holistic view of our body and spatial awareness. In this talk, I'll mainly focus on the spatial awareness application. Let me briefly introduce what do I mean by spatial awareness. So we introduce this idea of cocoon. The literal meaning of word cocoon is an envelope in a protective or comforting way. So the idea is that it will allow user to enable different application at different location. So it will enable user-defined situation-specific services. So when a user enters a cocoon, different functions would enable. So like if I am sitting on my desk and I'm working, it will automatically enable noise cancellation. And when I'm on my couch relaxing, then it will play some music or something like that. And this is done by profiling and detecting a location by audio signals, by the microphones that are present on our body will first sense the spatial profile simultaneously, and then we combine these spatial profiles to profile or detect a location. Before going into the microphone collaboration part, let me talk about what I mean by spatial profiling and how do we do spatial profiling with a single microphone. So say there is a speaker and there is a microphone, and the speaker emits an exponential sine sweep signal, and the microphone captures the signal and the reflections of the signal, which is the room response that it captures. And then if we convolve it with the inverse filter, which is the scaled version of time-reversed exponential sine sweep signal, we get the impulse response. That has information about the direct path and the reflections coming from various objects, walls, ceiling. And this impulse response will change with the change in microphone position. So if I place microphone at a different location, this impulse response will change. So we use this impulse response as for our spatial profiling. So we find this impulse response from multiple simultaneous on-body microphones, and we use that to detect a cocoon. So now we ask this question, why are we focusing on on-body microphone collaboration? Why are we looking into multi-microphone collaboration rather than a single microphone? So prior work has mainly done this kind of applications by using one microphone, which is mostly on our smartphone. But we are looking into multiple microphones. So the reason is that multiple microphone offers several advantages. The first one being enhanced spatial resolution. Since wearables are significant distant apart on our body, they can sense significantly different information simultaneously. So for example, in this particular application, in this particular image, on both the microphones, the dominant reflections arriving on both the microphones are very different. And we can see that in the impulse responses that they look very different. It also offers increased feature dimensionality. So since the microphones are sensing information simultaneously, we have richer information about the surroundings being sensed simultaneously. And robustness to slight movements and orientation changes. So we hypothesized that multiple microphones based system would be more robust because it's unlikely to cause significant difference in impulse responses in all the microphones simultaneously with a slight movement. So these are the advantages that multiple microphones would offer, but how would we combine these on-body microphone signals to profile a location? So there are several challenges in on-body microphone collaboration. The first one being synchronization. Since these microphones are present on different devices, the first step before collaboration would be synchronization, to synchronize the audio streams of these microphone signals. And all the variable device form factor, they do not support time synchronization. The second one is user movement. So when a user moves, variables move with them, so that will lead to change in the topology of the variable devices on the body, and it will lead to changes in orientation and positions, or relative orientation and positions, and hence it will lead to varying spatial profiles. And the third one is that the collaboration technique should maintain efficient and robust collaboration. So the collaboration should be able to handle missing and adding variable scenarios. So throughout the day, the number of variable devices on my body keep changing. So the collaboration should be able to handle that, and the collaboration cost should be minimal. So one easy way would be to send the entire data stream across the devices, but that might lead to high latency and energy costs. So in this paper, we propose a case study of on-body microphone collaboration using ear labels for spatial awareness application. And we use ear labels because ear labels are fixed distance apart, and they are relatively stable, and they are socially acceptable. Everyone has ear labels. So now I'll go into the details of how the system exactly works for the 2 ear label scenario. So first, we assume that there is a speaker in the vicinity that is emitting chirp signals. So the speaker is emitting the signals, and the microphones on both the ear labels, they capture the impulse response simultaneously. The chirp is 6 to 20 kilohertz, and once we have the impulse response being captured simultaneously, this is the first step, the spatial sensing part. We then look into synchronization. So for synchronization, what we do is we find the strongest and the direct path, and we clip everything before that. And then we also clip after 6,000 samples to avoid longer reflections. Next, to extract the features, we find the dominant peaks in the impulse response, which is left after spatial profile alignment. And for those peaks, we find the peak amplitude, peak time differences, peak times, and we do a feature ranking. So next comes the collaboration part, and for collaboration, we consider 2 techniques. The first one is feature concatenation, and the second is ensemble learning. The feature concatenation means all the features that are extracted needs to be transmitted to across devices, and then we train a comprehensive model on all those features collectively. And the second one is ensemble learning, where models are trained separately on each device, and then we aggregate the results. Due to the reasons that I mentioned earlier, that we need to handle adding and missing variable device scenario, and also we need to reduce the collaboration cost, we choose ensemble learning based technique. So for this reason, we first train a time series, KNN based time series classifier on each device, and we use dynamic time warping as the distance metric. And once the models are trained on individual devices, we aggregate the results by majority voting based ensemble learning. And that's how we detect a location, and then once the cocoon is detected, we activate its function. To prototype the system, we use 2 USB microphones placed on a ruler 20 centimeter apart, which is a typical distance between human ears. We could not use any commercial ear-able platform because no ear-able platform supports simultaneous microphone sensing from both the ear-ables. So for this reason, we use this as our prototype for controlled setup. For the real world setup, we clip the USB microphones with human ear, and we recorded data in multiple rooms and different locations. And it was observed that the accuracy with 2 microphones was higher than single microphone in both the controlled and real world setup. And in the real world setup, the accuracy was lower than the control world setup because since the microphones are clipped to human ears, there was more movement involved. And this validates our hypothesis that with multiple microphones, we can definitely get better accuracy because of increased feature dimensionality and enriched spatial information. To evaluate the robustness aspect, we recorded a subset of data in which we slightly moved the setup, and then we find accuracy on the entire data set and the subset of data set. And we observed that there was definitely accuracy drop with user movements, but the drop was lower with multi-microphone scenario than a single microphone scenario. Now I'd like to go through a few future work that we are currently looking into. The first one is that since our entire system assumes that there is a speaker present in the environment, to lift this assumption, we are looking into the sound sources that are already present in the environment, like the vent noise or other noises that could possibly eliminate the requirement of speaker in the environment. For now, the system is only implemented for 2 microphone scenario, but we would also like to extend the system to more wearable devices like smartwatches. When other wearable devices come into picture, the problem becomes more difficult because smartphone moves way more often than earable devices. And then we need to do continuous localization between earable, smartwatch. And the third one being, so to further ensure robustness of the system against user and environment factors, we would like to opportunistically sense spatial profile whenever the user is in the Cocoon, and then keep training our model online so that the performance improves with time. So to conclude my talk, we proposed Cocoon, which is a case study of using 2 microphone on-body microphone collaboration for spatial awareness application. And we show that how it outperforms the single microphone-based systems in terms of accuracy and robustness. Thank you for listening, and I'm happy to take any questions.
Nice talk, Bhavna. I have a quick question. So for the ensemble learning used majority voting, which would mean that whichever model gave you the best probability, you would go with that. Did you try other methods like averaging them out or like weighting them in some way?
Not yet, but yeah, like the weighting technique would be better if, say, for example, one microphone is more reliable in some scenarios than others, then we could do that kind of a technique.
Nice.
Yeah.
Okay, thank you.
Hi, this is Changshu from Singapore Management University. I have a question that is, do you consider about that the effect of the room size? Because if the room size is too small, there will be some echoes, and materials of wall because there is a different absorption factory of the sound. That's all.
Yeah. So we didn't look much into the room sizes. For our evaluation, we used 3 rooms, 2 conference room and 1 bedroom kind of a scenario, and all were mid-size room, not this big. And yeah, as you said, that some materials will absorb more. We are planning to look into the frequency domain of the impulse response and include that information, because that will give us information about which frequencies were more absorbed than others. So we'll definitely looking into include that information for our future work. Yeah.
Okay, thank you.
This is Yang Bai from University of Maryland, College Park. Very good work. And one question is, I'm wondering how big the effect is since in one picture you have 2 microphones on the chair. And if I rotate the chair a little bit, I assume the impulse response captured by the 2 microphones will also change a little bit, and how robust your system will be for that. And another question is what kind of signal you transmit to capture the impulse response.
Mm-hmm.
Thank you.
Yeah, so for the movement of the chair part, so for our evaluation, robustness evaluation, we just move the chair very slightly, but definitely if we move it a lot, then the impulse response on multiple microphones will also not be able to recognize the location. So for that purpose, what we propose is that if you keep sensing impulse responses from the multiple microphones while you are in that location, and if that doesn't match with the previous one, and you know you are inside the pre-registered location, so you keep updating your model using incremental learning or other techniques to make it better over time. And for your second question, we use chirps. We use two kinds of chirp signal. The first is the audible one, and the second is inaudible one. So the audible one is 6 to 20 kilohertz, and the inaudible one is 15 to 20 kilohertz. And there are no results of that here, but they are in the paper.
I see. So will the chirp signal from 6 to 20 kilohertz give you better accuracy?
Yes, it does
Yeah.
give us
Thank
better
you.
accuracy.
Hi, I'm Isaac Algren from Loyola University of Chicago. I was just curious, well, I know that a lot of consumer-grade mics have issues with nonlinearities in the mic. Do you guys deal with any nonlinearities trying to gather the impulse response in the room?
So in this work, we have only used microphones of same type. We have not explored different types of microphone. So maybe when we look into that, the nonlinearity will come into picture. And yeah, it will definitely affect it.
Yeah, it'd be interesting to see it on more IoT devices and lower consumer-grade mics.
Thank you.
All right, thank you. That will conclude our session, first session. Sorry for going over by 10 minutes. I believe there will be lunch. Don't know where they are, I think outside. And thank you very much again, and see you in the afternoon. Yeah.